now that we've defined exponents, we want to understand their broader properties. So what we're going to do is focus on a specific case that's overwhelmingly going to be the one that you're going to look at when you're doing courses in lower division. And it's the case where the base is positive, so we don't run into any nasty problems. So I'm going to look at what I'm going to call laws of exponents, so general properties of exponents, and we're going to assume that b is greater than naught. So what does that mean? So this implies that b to the x is defined for all numbers x, all real numbers x. So I'm going to make that assumption. Some of these will work for negative bases, but you'll have to be terribly careful about the exponents because of things like square roots, as we've seen. So the laws of exponents are, as I said, incredibly important. What you'll find is when you're doing calculus or other similar things, you'll be confronted with expressions that you need to rearrange into a different form. And to do that, you'll need to be familiar with the laws of exponents. So the laws of exponents, it's basically exactly the same as the laws, well, the properties of algebra that we looked in the first few videos, except it's about exponents rather than about your algebraic operations, plus, minus, addition, subtraction, multiplication, and division. It's about exponents, as I said. So these are general properties, ones that apply to any scenario. So let's start off with, first of all, the one that started it all going. Remember when I was defining exponents, I basically singled out two properties that seemed to hold when I was dealing with exponents, which were positive whole numbers. And really, essentially, I used those as a means to define the concept of an exponent or b to the n, where the exponent n was not necessarily a positive whole number. So the first was the property about multiplying exponents. So given the way we've defined things, it's no surprise that the following is true. B to the power a times b to the c is always equal to b to the a plus c. So multiplying adds the exponents. Okay, this is an incredibly important property. Incredibly important. So let's just see an example of this in action. So I want to give you examples which are kind of indicative of what you're going to see in your calculus classes and other things like this. So imagine I'm confronted with the following. Square root. So square root. So let's make this, let's copy it because we're going to use it a few times. So square root of x squared plus 1. Now before I do anything, x here represents a number. Is this a legitimate thing to write down? Well, yes, it is. X squared is always greater than or equal to 0, so x squared plus 1 is always greater than or equal to 1. I can always take the square root of positive terms, so I don't have any restrictions at all. But let's imagine that I was multiplying this, for example, by, instead of the square root, the cube root. So let's just move this down a bit. So same basic thing, but let's imagine a cube root here. Okay, now is this of the correct format? Well, it looks kind of different, but remember what these radical symbols mean. They're basically fractional powers. So this is equal to x squared plus 1 to the power of a half multiplied by x squared plus 1 to the power of a third. That's the definition of these. It's the meaning of the radical symbol. So this becomes what? It's exactly the correct format, with b is x squared plus 1, a is a half, and c is equal to a third. So this becomes x squared plus 1, a half plus a third. What's that equal to? A half plus a third is 5/6. Again, not jumping any steps, keeping it nice and simple. Everything is carefully written out. Okay, first law of exponents, super duper important. The base has to be the same for this to work. Now we can expand this a little bit to include negatives as follows. So this one isn't really very different than the one I'm going to write down. Isn't very different than the one I've just written down. It's good to have it slightly separated. So instead of a product, imagine I did a quotient. So imagine if I did b to the a divided by b to the c, this is equal to b to the a minus c. That basically follows because 1 over b to the c is b to the minus c, and then you just apply the previous property, but it's good to have this kind of written separately. Nice. This is true for absolutely any a or c. B is to be strictly positive in general, otherwise we could have problems, but this is a good general principle. All right, so let's do an example. So I'm going to do one very, very carefully, very slowly, just to illustrate how methodical you should be about this. So imagine I have square root, let's do x to the 4 plus 2. Same thing, I don't have any problems about square roots of negatives because x to the 4 is an even power, it's always positive. Plus 2, it's always greater than or equal to 0, sorry. And if I plus 2, it's always greater than or equal to 2, but that's certainly positive. Divided by, we'll do x to the 4 plus 2. Okay, let's write this out very carefully again. This is x to the 4 plus 2 to the power of half by definition, divided by, okay, well, x to the 4 plus 2 to the power 1 by definition. Now this is exactly the correct format, so this is equal to what? This would be equal to x to the 4 plus 2 to the power of half minus 1. So that would come out as what? X to the 4 plus 2 to the minus a half. So now I can invoke, if you want, this principle of negatives turning into reciprocals. This is 1 over x to the 4 plus 2 to the power of half. That's this rule again, really, with a 0 in front of the negative. So you could kind of think about that as kind of a 0 there, and then invoking the fact that anything to the power of 0 is 1, but I kind of leave it out of the notation. So now if you want to switch back to your radical notation, you would have this. So I know it's tempting just to, I mean, with a bit of experience, you might jump all these steps and go straight to the end. I think until you're at the point where you can do these in your sleep, you should really force yourself to write this as carefully as this. Okay, so that's a nice principle. What were the other properties? Well, the other one was when we took powers of powers. So powers of powers, how did that work? So if I took, what we do if I took b to the power a and I raised it to the power c, that's b to the a times c. We saw why that was true for positive whole numbers, and we basically used that as a way to kind of extend the meaning of exponents beyond positive whole numbers, but because we've done everything so carefully, it holds in general. So very important principle here. So let's do an example, shall we? I don't know, we'll do a really simple one. We'll do 2x plus 1 cube rooted squared. Now just a moment to take a look at this expression. Remember, x always represents a number. Does it make sense for any x? Well, I think it does, because you see 2x plus 1 could be negative, but we're taking a cube root, which is a 1 over 3, and 3 is odd. So that makes sense for anything at all. And of course, we can square any number we like, so there are no restrictions, nothing to worry about here. So this, if we're going to write this carefully, is 2 to the x plus 1 to the power third, all of that squared. So if we want to write this as a kind of a true fractional power, 2x plus 1, 2 over 3. Might be a useful way to write it down. Okay. So now let's think about what happens when I have different bases. So this is something which is not kind of turned up yet, but it's very important. So I maybe should make a warning here about this statement. I know I've made the assumption that b is positive, but some of these, like I said, do work on occasion when b is negative. You just got to be terribly careful about the exponents. So here's just a warning to show you this. This may fail. if b is negative, right? It may not be true. So let's just do a super simple example. Let's do minus 2 squared square root. So does this make sense? Well, minus 2 squared is 4. Square root of that is always the positive. Remember, it's equal to 2. And is that a problem? Well, minus 2 to the power, well, 2 divided by 2, if I was to multiply them, is equal to minus 2 to the 1, which is equal to minus 2. They're not equal to each other. So this fails. So you've got to be terribly, terribly careful. All right, so next, as I said, let's do different bases. So again, we'll always assume our bases are positive. If I take the product of two terms with the same exponent but different bases, this has to be equal to a times b to the power c. It's easy to see why that's the case if you have c, a positive whole number, because if I write c copies of a and c copies of b, I can intermingle them because a times b is b times a, and I could collect them and just observe the c versions, c copies of a times b. So it's kind of obvious for positive whole numbers, it's true the whole time. Again, to be safe, let's assume that a and b are positive. It will be true on occasion if a or b are negative, but you could have problems in general. So something to say here as well is if I write this in radical notation, which is often how it turns up, so assuming these radicals exist, which they will do here if I'm assuming a and b are positive, this is basically saying this. This is a special case. So you certainly need to be positive, otherwise terrible things could happen. So just as a quick example of this going on, so let me just box this important general principle. So as an example, if we had something like the cube root or the fourth root, let's be a bit more adventurous. Let's do the fourth root of 16 x squared plus 48. Imagine I want to kind of simplify this or something. So just as an example of this, you could write this as this guy, but I could factor out a 16 from inside. All right. Factor out a 16, but now I can apply this principle. I should say everything's positive. X squared is greater than or equal to 0, so x squared plus 3 is greater than or equal to 3, which is positive, so I don't have any issues. But this would be the fourth root 16 multiplied by the fourth root of what's left. So it would be x squared plus 3. And now that's just equal to 2. 2 to the 4 is equal to 16, so this is equal to this, yes, multiplied by this. Neat. That's just a standard calculation. Now this guy, of all guys, leads a lot of people into an extremely wrong assumption about how exponents work. So this really is saying that multiplication jives pretty well with exponents, but it's definitely not the case for addition. So this is a warning. Let me just put it down here. This is a major warning. This is the kind of mistake that can really derail questions in exams and things like that. So in general, it is not true that a, write it like this. It is not true that a to the power c plus b to the power c. This is not equal to a plus b to the power c. It's incredibly wrong. And in particular, if I was writing this with exponents, with radical notation, This is very much not equal to this. Like I said, this is like a very catastrophic error. I've seen many examples of people trying to take something that's difficult, trying to simplify in some way, and applying something like this, and it's just completely wrong, and everything kind of goes haywire from that point on. So let's just do a really simple example. 1 squared plus 1 squared, it's equal to, well, 1 plus 1, it's equal to 2. 1 plus 1 all squared is equal to 2 squared is equal to 4. They are not equal to each other. So that is not equal to that. Right? As I've said many times, if you are invoking some sort of algebraic principle, it better be true for numbers, right? That's what algebra is, right? It's frameworks that are general principles of how numbers work. So if you're invoking something and it doesn't work, then it's not the correct piece of algebra, right? So in particular, the square root of a sum is not the sum of the square roots, right? Really, really important. This is something to be really vigilant of because it's a major error. A major error. So final thing is, what about quotients? Well, what's going on? If quotients are very similar to what we've just done. If I have a to the power c divided by b to the power c, the exponents have to be the same. This can be written as a over b to the power c. Once again, let's be safe. This will be true in certain circumstances, but let's assume that a and b are positive. Otherwise, things can go haywire. Once again, we could write this in radical notation. Write this in radical notation. And that is equal to, assuming things are positive, so just quick example. If I was to do 1 over, so there are several ways to do the ones I'm writing down, but this is kind of a good illustration of this. If I do the cube root of x plus 1, do need to be slightly careful here. If I was to take the cube root of 0, it wouldn't work. So when I write this down, I'm explicitly or implicitly assuming I'm not equal to 0. So x plus 1 is not equal to 0, i.e. x is not equal to minus 1. So what I'm writing down only makes sense for x not equal to minus 1. So let me write this down as 1 to the power of third. It's kind of a strange way to do it, but it's going to fit nicely with our previous, or what's on the left-hand side. So I've got this. And now this is equal to what? Well, I tell you what, I should be careful here because I'm not 100% certain this is going to work, this formula, but let's be safe. Let's be completely safe and let's assume I'm positive here. It will actually be true. It will actually be true for negative x plus 1, but it doesn't quite fit with the pattern. It's a little more dangerous. So let's assume x plus 1 is positive just to make sure we are really fitting with this story. So this becomes what? 1 over x plus 1 to the 1 over 3. So if I want, I could write this whole thing as cube root of 1 over x plus 1. So maybe just to say for negatives, this guy will work for negatives as long as n is odd. Okay, it's totally fine. If n is even, it's not going to make sense because if n is even, if either of a or b is negative, it won't make sense. And for an equality, both sides need to make sense. So that's just something to be aware of. So maybe I'll just write this down. This does work. Works for a and b negative, potentially, if n is odd. Otherwise, it doesn't work. Okay, so let's just recap. We basically have five laws of exponents. It's not a huge number. Some of them are very closely related. The first is the product of exponents with the same base corresponds to the sum of the exponents. The quotient corresponds to the difference. A repeated exponentiation, so raising to the power a then to the power c, is the same as raising to the power a times c. With different bases with the same exponent, they kind of come inside. It's very nice. Same with the radicals. It absolutely does not work with addition. Super important. And with quotients, it's essentially the same. So those are the laws of the exponents. It's not a huge number of different things. You must be familiar with each of these. This is a key tool you're going to use to simplify complicated expressions. Without them, you're going to really struggle to do challenging examples.